Hi, I'm Vinitha Gadiraju. I am a PhD student at the University of Colorado Boulder, and today I will be presenting our Chi paper, Braille Blocks, Computational Braille Toys for Collaborative Learning, on behalf of myself and my co-authors, Annika, Muehlbradt, and Shaun, Kane. So experts have found that Braille literacy is declining among blind students in the US. In 1960, over 50% of blind students were identified as Braille readers. However, in 2017, only about 8% of blind students in the US were identified as Braille readers. A possible catalyst for this decline includes rising accessible technology that present other methods of reading, like audiobooks and text-to-speech technology. However, even with alternative reading methods available, education experts have found that Braille literacy improves reading comprehension skills and increases chances of employment for visually impaired people. However, learning Braille can be tedious and difficult and an isolating process for students. Our goal is to build tools that encourage visually impaired people and sighted people to learn Braille together in fun and engaging ways. Games can motivate children to interact with Braille and build fun learning experiences. Researchers have created Braille games and mobile applications to teach basic Braille concepts. Braille Play, G-Braille, and M-Braille use haptic feedback on a phone's touchscreen to represent a Braille cell and the dots in the cell that make a Braille letter. These applications include audio-based games like Hangman to practice spelling and letter recall. In the image on screen, there is a mobile Braille cell representation from the Braille Play interface. Users can double-tap one of the 6 dots on screen to raise that dot in the Braille cell. Users can use a 2-finger swipe to submit the letter. There is a small selection of Braille toys for visually impaired children to play with, many of which are block-based. The top image is Braille Bricks, a commercial product that LEGO is releasing this year. Braille Bricks are Legos with slightly enlarged Braille on the surface. Students can place Legos together on a mat to build words and sentences. In the image on the bottom right, we can see a similar approach from the company Tactiles. Tactiles uses Lego-sized blocks with Braille on the surface. There are also larger blocks with both print and Braille, as seen in the image to the bottom left, of Plan Toys' Braille A to Z alphabet set. Blocks and tangibles have also been used outside of Braille education for visually impaired children. In particular, interactive tangibles have been used to teach the basics of programming. The image on the left shows connectable pods and the interactive programming application from Microsoft's CodeJumper. CodeJumper uses a set of connectable pods to enable children to construct programs that represent music and other audio. The image on the right shows Storyblocks, a set of code blocks that students can assemble to program fun audio stories as output. Each of these systems combines tactile interaction with audio output to create an engaging and accessible learning experience. BrailleBlocks draws inspiration from current Braille toys, game applications, and tangible computing, and applies the overall approach of interactive tangible blocks to Braille education. BrailleBlocks is a smart toy block set that supports interactive games by tracking the blocks and providing audio feedback for everyone and visual feedback for parents. The top image on screen shows the 3 components of BrailleBlocks. The first component of BrailleBlocks is the tangibles, which includes the blocks, pegs, and a frame that contains the blocks. The second is the associated web application. And the third is an overhead webcam to track the blocks. The bottom image on screen is a close-up of the BrailleBlocks tangible set. A Braille cell contains 6 dots that are numbered top to bottom, left to right. This is shown with the Braille blocks in the image on the right. A Braille letter is determined by which dots are raised, or in this case, which holes have pegs in them. We chose to make enlarged blocks, rather than standard size, to support children still working on early motor skills, so they can easily grab the blocks and physically construct letters using the pegs. The image on the left shows the dimensions in inches for a single Braille block. The block is 1.25 inches high, 2 inches wide, and 3 inches long. Each block in the tangible set represents a single Braille cell. Children can place pegs in the block's holes to build Braille letters. They can then place blocks together to create words. In the video we just saw, we saw a user placing pegs in dots 1, 3, and 5 of the Braille block to create the letter O. Each game in the system has a check word feature. This connects to a computer vision program we wrote to help parents and other players who are not familiar with Braille determine what letters the child has built. When parents press the check word button shown at the top of the screen, The overhead webcam takes a picture of what the child has built. The picture of the blocks and pegs inside the frame taken by the webcam is shown at the bottom of the screen. In the computer vision program, first we clip the image using 4 colored markers on the edge of the frame. This is shown in the image at the top of the screen. Then we apply a mask to extract all the red from the image. This is shown in the image in the middle of the screen. From there, we can determine what letter the block represents, and the system outputs the letters in a dialog box on the interface for parents to check what the child has built. The dialog box is shown at the bottom of the screen, outputting the word elephant. The system includes 3 interactive games. The first is the animal name game, which uses audio clues to practice spelling. The image on the left shows the animal selection chart from the animal name game, with images of a dog, elephant, duck, and sheep. The second is Hangman, which uses audio for correct and incorrect letter guesses. The main screen from this game is shown in the image in the top right, which has a text input form and a set of interactive buttons. The last game is a word scramble that works on tactile letter identification. Level 1 of word scramble is shown in the bottom right image on screen. The image has Braille representations of the letters T, C, and A, along with some words the letters can scramble to make, like act and cat. So this is a video walkthrough of the animal name game. Parents select elephant from the animal selection chart described earlier, and then play the animal sound. That was an elephant noise. Now the child is building the word elephant with the blocks and pegs. And then parents can check what the child has built using the check word feature. And so on screen, we can see that the dialog box says elephant. So in Hangman, parents can enter a goal word and then play a ding for a correct guess and a buzzer sound for an incorrect guess. So the word that was entered was pickles, and parents can use the check word feature to check what their child has built in this game as well. So there are 5 levels in Word Scramble, and they each increase in difficulty. So in this video, the parent selects level 1, and there's a visual Braille representation of the letters T, C, and A, along with the words that they unscramble to make, act, cat, and at. Parents can also use the check word feature here to see if the child has unscrambled the letters correctly. So we conducted a usability study to observe how sighted parents and visually impaired children collaborated and learned with Braille Blocks, and to collect feedback about our existing prototypes. The image on screen shows one of our participant families using the system. On the left are 2 visually impaired children, and on the right is their sighted parent. The study consisted of individual sessions with 5 participant families. 4 of these families had 1 sighted parent and 1 visually impaired child. 1 family had 1 sighted parent and 2 visually impaired siblings. There are cartoon drawings on screen with a parent and child representing each of our participant families. We asked participants to explore the games I outlined earlier and encouraged them to use the system however they felt best addressed their child's Braille literacy level and learning styles. We suggested starting with the animal name game, then Hangman, and finishing with the word scramble to have gameplay that got increasingly hard, but ultimately parents played however they wanted. After participants explored the games, we conducted an interview to gather feedback on the system and learn more about families' current Braille practices and experiences with Braille tech. In the findings, we look at guidance techniques that parents use with their child, how parents adapted the games, what skills were built during gameplay, participant engagement and feedback, and concrete improvements to the system. So one theme that emerged from our studies was that parents often used physical guidance with the system. Parents took an active role in helping their child find and feel the blocks. Parents would place their hand over their child's hand and feel each hole in the block while counting the numbers of the Braille cell. They also did this to orient their child with the distance between blocks, as well as the cardboard frame. The image on screen shows one of our participant families using the hand-over-hand technique to feel the holes in the blocks. While we provided general instructions on how each game could be played, parents took control and adapted the games for their child's grade level, Braille knowledge, and skills that they wanted to work on. Particularly, parents use the system to build learning skills beyond recognizing and making Braille letters. For example, parents used the animal name game to practice spelling. 2 of the families used Hangman to practice name spelling, which they identified as a key skill for kindergarten and first grade. And parents use the blocks to help their child work on phonetics and sounding out full words. Parents often use the games as guessing activities and provided hints to help their child deduce answers. So during Hangman, parents would provide their child with hints like, "This is the name of a dog we know," or "This is your favorite food," to encourage their child to guess through different words rather than guess letters like the traditional Hangman game. In Word Scramble, parents similarly provided hints for the words their child could not unscramble on their own. The hints here took on a fill-in-the-blank form, with parents asking, "Where are you blank?" for the word at, and "You drink hot blank" for the word tea. Many parents and children reported Hangman as their favorite game. Parents and children were entertained by the audio feedback and sound effects provided by the games. For example, they would laugh every time they heard the incorrect buzzer in Hangman, and the children kept screaming, "It sounds like a fart." Children would guess silly things like 3, so their parents would play the sound repeatedly. Parents would also add in their own sound effects, especially in the animal name game. So beyond learning skills, we found that children just liked playing with the blocks. While their parents filled out consent forms or during the interview, children would build friend structures using the tangibles. For example, the participant in the image on screen built a mansion using the blocks, where the pegs were people living in the mansion. The people took the train to work every day, where the train was the cardboard frame and work was the overhead webcam. It was really encouraging that children were motivated to use the system to supplement their learning with creative play and storytelling. So we asked both parents and children about their engagement while using the system. Engagement among parents tended to be pretty high, while engagement among children seemed to vary depending on how comfortable the child was with Braille. There are emojis on screen representing parent and child engagement from a scale of 1 to 5, with 5 being the most engaged. 4 parents reported the highest engagement of 5, and 1 parent reported a 3. 3 children reported a 5, 1 child reported a 4, and 2 children reported a 2. So parents told us their thoughts on what they appreciated about the system, and one of them is that they felt like the system supported dual readers. One parent noted, "Having things like this where you can see the Braille and feel it is really helpful. I love the idea for kids who still have enough vision to look at the Braille and feel it to build their visual memory." Parents also liked the adaptability of the system to where their child was at, and even thought it could be used again for grade 2 Braille. Parents thought that BrailleBlocks was a fun toy option for visually impaired children. One parent was saying, "We are always talking with other parents about what to get our kids for Christmas. Like other kids, you get them Uno cards, but this would be great." So we received concrete feedback on the prototypes themselves to improve learning. Parents suggested adding a tactile marker on the block to orient the top and bottom of the block. They also suggested more audio feedback for children so that they could play independently. For example, with the check word feature, rather than just showing a dialog box to parents, parents suggested including an audio description of what the child built. Alternatively, they suggested that the system could provide minimal feedback through sound effects, indicating when a child had built a letter word incorrectly or correctly, kind of like Hangman. Finally, parents suggested generating student progress reports to help track learning with the system. From the findings, our main takeaways were that participants used the games to build Braille skills like letter recognition and identifying which dot numbers make up a letter. Participants use the system to build learning skills beyond just Braille, like spelling and reasoning. And children use the tangibles for creative play and storytelling. Finally, participants were entertained by the sound effects and audio feedback in the system and expanded on the audio by creating their own sound effects. In our future work, we will look at how we can adapt Braille blocks for classroom learning. We will work with teachers of the visually impaired to identify literacy learning outcomes, and we will also look at how the system can be played in groups of peers and monitored by educators. Since learning has started to move online, we will also explore how to build tools that support remote classrooms for visually impaired children, as well as enable virtual collaboration and play the system, like with sighted grandparents over Zoom. So thank you for taking the time to listen to this work. I would once again like to thank my co-authors and advisor, Shaun, Kane, my lab mates in the Superhuman Computing Lab for their support, and our participants for collaborating with us on this project. I have linked all of our Twitter handles in this slide, so if you have any questions or comments, feel free to tweet at us or direct message us. Thank you.